This is slide number 3 of the course on Fourier optics, and I am your presenter Asloob Mudassar. Optical field. Optical field is very important in Fourier optics. Again and again and repeatedly we shall talk about calculation of optical field in some region of the optical systems or at the image plane. So optical field is very important quantity that we shall be repeatedly calculating it through the rest of our course. And you know that light in terms of amplitude and phase, also known as complex field. The proper word is complex field because it contains amplitude information and phase information, for example on a given plane. And we shall be referring this complex field as the optical field, or simply the word field will be used. So whenever you come across the word field, it means that we are talking about the optical field, and optical field means that we are talking about the complex field. And complex field means that of course we have the information of the amplitude and phase. It means that in the calculation of the optical field through any optical system, through any physical optical system, we shall be calculating the amplitude and phase information at a given plane. And you should remember that optical field is not a physically measurable quantity. That is, when we try to measure it, you lose the phase information, because all detectors are intensity detectors, and when the intensity detectors measure the optical field, the phase information is lost, because we calculate there the absolute square of these physical quantities. And since in the absolute square of these physical quantities, the complex part, that is the part with iota, is that is cancelled out or vanishes from the expression, and we get just only the amplitude square of those when we are physically measuring the quantities. But you know that sometimes it is required to measure the phase value and the phase information and the amplitude information together in an optical system. For that, special techniques such as holographic methods are used to record the complex field. Intensity, as you know that intensity, how the intensity is related with the complex field, that is simply given by a physical detector measures only the square of amplitude. So phase information is lost during the measurement, and you know that the intensity expression is given by optical field multiplied by the complex conjugate of that optical field. And so you know that when we compute this expression, we get the intensity, that is, we get the square of the amplitude, and the phase information is lost there. The next one is so let's talk about more about the light sources. Before that, we have talked about the coherent and incoherent waves. Coherent field mean so you know that now I am talking about the word field. Coherent field mean that on a single plane there is a fixed phase relationship between different parts of the plane. So if the phase relationship is fixed, we say that we are talking about the coherent wave or the coherent field. But if there is a variation of the phase relationship, that is the mutual phase relationship does not stay constant, then we say that we are talking about the incoherent field. Monochromatic mean single color. So you know that monochromatic doesn't mean that a single wavelength. So a large wavelength, a large number of wavelengths. For example, if we are talking about the red region, red, you know that is monochromatic, but you know that in the red we have a large number of spectral band and we have a large number of wavelengths there. So, but you know that this is a misconception that a monochromatic means a single wavelength. So you should use this word with caution. So next is polochromatic and narrow band. Polochromatic means that many wavelengths are present, but it is narrow band. For example, helium neon laser, which is operating with wavelengths containing, for example, 20 different wavelengths in its spectrum, may be regarded as a polochromatic and narrow band. And when we say that polochromatic broadband, it means that, for example, the sunlight is or the light from our sources in our homes and in our offices, they are polochromatic broadband sources, contains a range of wavelengths in the visible spectrum, and the spectrum is also very broad. So that is polochromatic broadband. A perfectly monochromatic source does not exist. For example, even a high quality laser source is far from from being monochromatic. So let's talk about a very high quality laser source. For example, a very high quality laser source, or for a high quality helium neon laser source, may be operating at 3 different wavelengths. So you know that we cannot reduce by any special means, we cannot reduce those 3 wavelengths to be operating at a single wavelength. That requires very hi-fi and very skilled qualities in order to obtain a single wavelength. So even a single wavelength will have some broadening. It means that it will also be some other wavelengths are also coming with that one. So simply speaking, that if we talk about a perfect monochromatic source in terms of a laser beam, you may consider that for example 3 wavelengths are coming with that one. So we would say only that a perfect monochromatic source would not exist. Here we end presentation number 3.